So it is a pleasure to have Dominique Attali today, and she will tell us about the Delaunay-like triangulation of smooth orientable submanifolds by L1 non-minimization. And also she said she's okay having question right away, so feel free to ask. Okay, go ahead.
So thanks a lot for the invitation. And I'm going to present a work that is a joint work with André Lieutier. So we are interested in the following problem. We have a shape, which is a subset in some n-dimensional space. And this shape has been sampled. And so we have as an input a bunch of points, P. And given as input those points, we would like to construct a mesh that provides an approximation of the shape. So typically in 3D, the shape can be the boundary of a physical object, and then we would have major points on this boundary. But this problem arises in manifold learning. And in that case, people often do the assumption of a machine that we are learning a manifold. And why is that? Because so we are in a high dimensional space. We are measuring plenty of variables, but the phenomenon that we are observing typically has a small number of degree of freedom. And so we expect the points that we are measuring to lie on a low dimensional submanifold. Okay, so it is reasonable to assume that the shape we are considering is some smooth d-dimensional submanifold of Rn. So again, we have measured points on that shape, on that submanifold. And what we would like to construct is some simplicial complex whose vertices are going to be our data points, our points in P. We would like this simplicial complex to be embedded and to define a domain that will be homeomorphic to the shape. So this is what we're going to call in this talk a faithful reconstruction. So we would like the output to capture the full topology of the shape. So what can be done is to construct first an auxiliary construction. Typically, it can be the alpha complex of the point set P at some scale parameter, at some scale rho, or the Rips complex of the point set P for some parameter rho. And it is known that those constructions under some conditions are able to reproduce the homotopy type of the shape. So starting from those auxiliary constructions, one could try to simplify them until we obtain something that will be homeomorphic to the shape. And typically, one would apply some collapses. For instance, this is the principle of the wrap algorithm proposed by Edels-Brunner to reconstruct surfaces in 3D. But here in this talk, I'm going to present another approach. So this will be a variational approach. So we don't assume anymore that our auxiliary construction has the homotopy type of the shape. This is not necessary. What we want to do is to search a solution within this auxiliary construction by and express the faithful, the output as the solution of a minimization problem. So for this, we are taking inspiration from the Euclidean case. So suppose for a moment that the shape is actually has no curvature, is a D flat, and that the points lies they lie on that flat. Then we know how to build a faithful reconstruction of the convex hull of the points. For this, we just construct the Delaunay complex of the points. And we know that when the points are generic, this will provide indeed a faithful reconstruction of the convex hull of the points. And what is nice is that this Delaunay complex has a geometric characterization of its elements, but it also has a variational characterization that I'm going to describe. So yeah, we know in particular that this Delaunay complex minimizes the Delaunay energy. So I'm going to define the Delaunay energy. So take a triangulation T of a point set P in RD. And we're going to associate to this triangulation T a Delaunay energy. For this, we use a lifting construction. We are considering a paraboloid in RD plus 1, whose equation is given above here. Yeah, which is the graph of the map whose function is the square of the point. Okay. And so we take the point set P, we project vertically those points onto the paraboloid, and we get a set of lifted points. And sorry for that. Yeah, and then we lift the triangulation T. That is, for each simplex sigma in the triangulation T, we lift the vertices, and then the lifted simplex is the convex hull of the lifted vertices. So to a triangulation T, we have associated a lifted triangulation T hat, and now the Delaunay energy is the volume between the lifted triangulation and the paraboloid. And this volume is known to be minimized when the triangulation T is the Delaunay complex. And it turns out that this Delaunay energy has a nice expression. It can be expressed as the sum over all these simplices in the triangulation T of the volume between the simplex lifted and the paraboloid. And this volume that has been represented here in yellow is what we call the Delaunay weight of sigma. And this Delaunay weight, this volume, has a nice intrinsic expression that was obtained by Shen and Host in 2011. And this expression depends upon the dimension, d, the volume of sigma, and the length of the edges of sigma. So this means that actually here we can, when we have a soup of triangulation T formed of these simplices that lie in a higher dimensional space in Rn, we are still able to associate to this soup of these simplices a Delaunay energy by just making the sum of the Delaunay weights of its d simplices. And so this was really the starting point of this work, this observation. Okay. So here we would like to mimic exactly what we saw in the Euclidean case to the manifold case. That is, now we are going to consider a shape that is a smooth d-dimensional submanifold of Rn. We're going to consider point set P that sample M, possibly with some noise. And we're going to define, we are going to consider a scale parameter rho and define a complex that we're going to call the d-dimensional Delloc complex of P at scale rho. And we shall provide both a geometric characterization of its elements and also a variational characterization. And we shall see also that under the right conditions, this Delloc complex will be a faithful reconstruction of the manifold. Okay, so this gives us a plan, a roadmap for the talk. First, we're going to define this Delloc complex. Second, we are going to state conditions under which this is a faithful reconstruction of the manifold. Third, we are going to describe a minimization problem. And fourth, we are going to state conditions under which this minimization problem is indeed the Delloc complex. So when we started this work, we were having a clear idea of the minimization problem we wanted to consider. And so we tried to study the solution, and the Delloc complex was perfect for that. But this Delloc complex is actually very close and may coincide under the right condition with the tangential Delaunay complex that has been studied by Boissonnat, Gauche, Dyer, Wintreichen, and a long list of authors. Yeah, but since for us this is really this Delloc property that is important, I'm going to, in this talk, to introduce this Delloc complex. So for first, I'm going to define what we mean by a Delloc simplex. So for this, consider a simplex sigma that is a non-degenerate abstract d-simplex in Rn. So really, sigma is a finite set of vertices. And we're going to assume that sigma is a rho small. Rho small, this would be a way to say that sigma is enclosed in a ball of radius rho. So now consider the smallest ball that contains sigma, and let's say sigma be the center of that ball. Consider the ball center that this center, say sigma, and whose radius is rho. So by construction, because of our assumption, this ball is going to contain sigma, but it may contain also other points of P. And we are going to call those points inside this ball, those points of P inside this ball that are different from the vertices of sigma. We're going to call them the neighbors of sigma at scale rho. So this is the blue points that you can see here. And now we are going to project those neighbors onto the affine space spanned by sigma. And what we obtain is a bunch of points, the red points there, that we're going to call the landmarks of sigma at scale rho. And so a simplex sigma is going to be a Delloc, Delloc at scale rho if the circumsphere of sigma does not enclose any landmark of sigma. So in other words, sigma is going to be a Delloc for P at scale rho if sigma belongs to the Delaunay triangulation of the landmarks to which we have added the vertices of sigma. So locally, you can see that to decide if sigma is a Delloc simplex, we have constructed locally in the affine space a faithful reconstruction. Also, really, the idea is that if the set of points P sample the manifold sufficiently densely, then to decide if the simplex, if we have to keep sigma in the reconstruction, that is, if it's a Delloc simplex, it should make no difference to replace the manifold by the affine space spanned by sigma, and it should also make no difference if we replace P by the landmarks of sigma. So that's the idea. And so now the Delloc complex is going to be the Delloc simplices together with all the faces of those Delloc simplices. And so we get a construction, and the question is it a faithful reconstruction? So unfortunately, it is not always, because of slivers that may appear. So let me explain this. Suppose that you are in 3D and the manifold is a surface, and you consider 4 points, A, B, C, D, that form a sliver. That is, they are almost co-circular. They are, they're closed from this yellow circle, say. And what may happen is that whenever you pick 3 vertices among the 4s, they're going to define an affine space, okay, a plane. And when you project the 4th points, this 4th points is going to be contained, to be enclosed in the circumcircle defined by the 3 others. So it will happen that none of the faces of this sliver is Delloc. So we are going to miss the 3 triangles of this tetrahedron, and this is, in our construction, going to create a hole. And so this is not going to be homeomorphic to the surface. So here is what may happen. And so to avoid this, we will have to control the projection of simplex. So what do we call the protection of a simplex? It's a quantity. So the protection of the simplex sigma at scale rho is going to be the distance between the landmarks of sigma and the circumsphere of sigma. So we want this quantity to be large enough to avoid the existence of slivers in our point set. Okay. We will also need to express conditions under which the Delloc complex will be a faithful reconstruction. We will also need to control the angle that the simplex sigma makes with the manifold. So precisely, we will say that given a point M on the manifold, the tangent plane passing through M is nearby the simplex sigma if M belongs to the projection of sigma onto the manifold. Okay, and we call the angular deviation of sigma at scale rho the maximum angle that the affine space spanned by sigma makes with a nearby tangent plane. And so we will want this angular deviation to be sufficiently small. So we are almost ready to state our first result. So we have again M, which is going to be, we're going to assume to be a compact C2 d-dimensional submanifold of Rn. We recall that the reach of this manifold is the distance between the manifold on its medial axis. And the medial axis of a set is the set of points that have at least 2 closest points in the set. So here in red, we have the medial axis of the black curve M, under which maybe is represented by the length of this segment. Okay. And so our first result is that it states conditions under which the Delloc complex is a faithful reconstruction of M. So first, we have sampling conditions. So they depend upon two parameters, epsilon and delta. Epsilon is going to control the density of the point set, and delta the accuracy of the point set. Okay. So yeah, and together with those sampling conditions, we have also safety conditions that I'm not going to describe in the details. So what they say is that the point set P has we want the point set P to be sufficiently separated. That is, the points, they must not be too close from one another in the point set P. The 3-row small d simplices of our point set P must have a sufficiently large protection. And the angular deviation of row small d simplices in P must be small enough. So, okay.
Dominique?
Yes.
I have a quick question. So faithful reconstruction of M means that the simplex is homeomorphic to M. Am I correct?
Yes.
Or homeomorphic.
Homomorphic,
okay.
yes.
Okay, thank you.
Yeah.
I have a question as well. So as you explained, it's the protection hypothesis that rules out this problem of slivers.
Yes, exactly. Yeah. So it's yeah, it's there exactly to remove the problem of slivers. On the angular deviation, yeah, I'm going to explain, yes, why we need that in a second. Okay, and you see also that those conditions, they are expressed relatively to the reach of M. Okay. So in a glimpse, what is happening? So we have those sampling conditions that are totally, completely reasonable, plus some safety conditions. So a point set P that you receive may not enjoy those safety conditions. You may have to perturb the point set P so that it's going to enjoy those safety conditions at scale rho. And then if you have the two, then you get a faithful reconstruction of M. And so the idea is that locally you have faithful reconstructions because locally you take Delaunay simplices in some affine space. And taking all those faithful reconstructions locally, you have to glue them in such a way that globally they form a faithful reconstruction. And here, the angular deviation is going to be important because we will need to glue everything together and apply in particular some stability results from Boissonnat that says that as you perturb the vertices, that gives you conditions under which when you perturb the vertices of your point set, the Delaunay complex is going to remain stable. Okay. So now I would like to describe the variational approach, variational characterization here. So for this, we are going to assume that the shape M is furthermore orientable. This is going to be key. And okay, so we would like to mimic what happens for the Delaunay complex, which minimizes the Delaunay energy among the triangulation. So a very naive formulation would be to say that we would like to find a set of d simplices T that minimize the Delaunay energy subject to the fact that T is a faithful reconstruction of M. Of course, this is highly non-convex, and we would like to transform this into a convex problem. So how we do that? We're going to assume, furthermore, that we have a simplicial complex K with vertex set P, and that that can be interpreted as a row approximation of M. And we're going to look for a solution inside K. So for this, what we do is that we are going to enlarge the search space. That is, we're going to replace the set of triangulations of M, which is with vertices points in P, and this set is finite. We're going to replace this finite set by a vector space, which is the set of D chains of K with coefficients in R. So here is the situation. We have M, we have our point set P, and we have represented K on the right. So M is orientable. So we are going to pick an orientation for M, and we're also going to assume that K is close enough to M so that we can transfer this orientation from M to all simplices in K. So this is really just for the explanation, and in practice, we don't need to do that. So for the algorithm, we don't need to have access to this orientation. Okay, so this is what we've done here with the blue arrows. And now an element, a D chain, is just a vector that can be expressed in the basis formed by the D simplices of K. Okay, and to this vector, to this D chain, we're going to associate a real number that we're going to call the load of this D chain gamma at the point M0 on the manifold. So we pick a point M0 on the manifold, and we select in K all the simplices whose projection onto the manifold contains M0. So another way to see that is that you take the normal to the manifold at M0, you restrict it to, say, a segment of length 2 times the reach, and you look at all the simplices of K that intersect this segment. They are represented in pink here. And then you take the coordinate of the chain gamma on those pink simplices, and you take the sum. And this is so the load of gamma at point M0. So now if you consider a faithful reconstruction L contained, a faithful reconstruction of M contained in K, to this faithful reconstruction, we can associate a particular D chain, which we are going to call the code of L. And this D chain is going to take a coefficient 1 if for all simplices sigma, D simplices sigma that belongs to L, and 0 otherwise. And it turns out that the code of L, because L is a faithful reconstruction, enjoys two properties. Its boundary vanishes, so this is a cycle, and the load also computed at any point M0 is going to be equal to 1. So this property, we are going to say that the code is normalized. And so this gives us the idea to restrict the search among all D chains gamma for which are cycles and which are normalized. Except that if you're not careful, you may get a chain. There is no reason that the chain you get is the code of something, because the coefficients, they have no reason to be equal to 0 or 1. So this is the reason why we are using, for the optimization, an L1 norm. So we are going to minimize among all D chains. We are going to minimize the Delaunay energy of a D chain gamma. And this Delaunay energy, we're going to define it as the weighted L1, as a weighted L1 norm, where the weights are the Delaunay weights that we have defined before. And so we are going to consider the problem, which minimize this Delaunay energy among all D chains that are cycles unnormalized. So one can see that under this form, we get a least norm problem whose constraint functions are linear. So this is a convex optimization problem. And so we've done some experiments. So here you can see the for point sets that are, for point sets, we've computed the Rips complex. We've used the Rips complex as K. Then we computed the harmonic form, which is known to spread everywhere on K. And then we started to minimize to find the smallest, the D chain with the smallest Delaunay energy that is represented on the right. And so there is a code color. When a simplex has a coordinate which is close to 1, it's blue. And when it's close to 0, it's rather white. So you can see that in the first two examples, we obtain indeed a triangulation of our point set. But in the last example, probably the curvature was too important compared to the density. And so we obtained a chain that was spreading, yes, at the tips of the... And so here is our second result. So the second result, I've highlighted the result. So the problem I've just presented has indeed a unique solution, which is a faithful reconstruction of M. Actually, it is a code for the Delloc complex that we've defined before. And I'm going to go to state so all the conditions that we need. So first, K, how is it defined? We just need K to be large enough to contain the Delloc complex. So it suffices, for instance, that K here contains the check complex of P at scale epsilon, that is the set of epsilon small simplices of P. And you can intersect it, for instance, by the Delaunay complex of P. So, okay. And it suffices also K must not be too large. It must be contained in the check complex of P at scale rho. So K, the K that you can choose, the constraints are not that are mild. It has to be large enough, but not too big. Okay. And then again, you find for P, the sampling conditions that are defined by delta and epsilon. So P must be both sufficiently dense and sufficiently accurate, epsilon dense and delta accurate. And then you require the safety conditions that we saw before, together with an additional condition that is stated here, that is, okay, horrible, but appears when we did the proof.
Dominique, I missed
Yes.
I think I missed something. What is K here precisely?
So K is a simplicial complex that you build, that you know how to build easily from your point set P. Typically, it can be the check complex of P intersected with the Delaunay complex. For instance, if you are in small dimension, you would choose that. If you're in a high dimension, you would probably take for K complex that could work for K is the Rips complex, typically, for a scale parameter that is between epsilon and rho. Yes. Where rho has to be somewhere larger than the density and smaller than the reach. I don't know if it answers your question.
Yeah, sure. Thank you.
So I think that my time, So what does it say? It says that you have your sampling conditions your safety conditions, and then the problem that I just stated has a unique solution, which encodes the Delloc complex. And so the idea is that the Delloc complex has been defined precisely so that locally it's a minimizer. And what happens here is that everywhere you take a local minimizer, and so it seems really reasonable that globally it should be also a minimizer. But proving this turned out more tricky than it seems. And so here I'm going to skip this because I wanted to explain a bit the proof, but I don't think that I have time for this. Yeah. Maybe in conclusion, so we have this result. We know that it's possible to define a faithful reconstruction by minimization. And what would be nice now would be to focus on algorithmic aspects. That is, how to do in practice, can it be competitive? So thank you, if you have questions.
Okay, I think we can unmute ourselves, and thanks to Dominique for the wonderful talk. Thank you.
Thanks.
So any questions?
I'll start with a question. Sorry, we're probably too stringent with our time suggestions. I would be interested. Could you explain the idea of the proof? You know,
Yeah, because
yeah.
okay. If you have, I didn't want to to take too much time, but if you want, I can explain this to you.
Yes,
so
please.
So the idea of the proof is the following. First, I'm going to describe the proof, the idea of the proof in the Euclidean case. And then I'm going to explain why it was complicated to go from the Euclidean case to the manifold case. So in the Euclidean case, it's useful. So I've written the definition of the Delaunay weight here that you can see, and that is associated to a simplex sigma. And it's useful to give another geometric interpretation of this Delaunay weight. And for this, you're going to associate to a simplex sigma here a paraboloid in Rd plus 1. So sigma has dimension d, and I'm constructing this paraboloid in Rd plus 1 in such a way that its axis is vertical. It's going to pass through the circumcircle of sigma. On the height, the highest point of this paraboloid is at height the circumradius of sigma square. And it turns out that if we consider just the part of this paraboloid that is above sigma, we're going to call this the dome of sigma. The Delaunay weight is precisely the volume above sigma and below the dome. So it can be reinterpreted like this. So when we have a triangulation T in Rd, now for each D simplex sigma, it has a dome, the dome of sigma, and we can associate to a triangulation T a surface that is formed of this union of small domes, like this. And the Delaunay energy of this triangulation is the volume above the convex hull of the point set, above T, and below that surface. And when we consider triangulation T, which is the Delaunay complex of P, this surface tends to be the lowest possible, because the Delaunay energy is the smallest in that case. And so how we can see that precisely? So consider a simplex alpha that is Delaunay, and a simplex sigma that is non-Delaunay, the blue one here. when we look at the domes of alpha and sigma, the following happens. Wherever the convex hull of sigma overlaps the convex hull of alpha, then the dome of sigma is going to be above the dome of alpha. And this can be represented here in 1D. So in 1D, I've represented the Delaunay complex of P. I've represented alpha, which is a Delaunay complex, in that case, 2 consecutive points, the dome of alpha in pink, and then I've taken a simplex sigma that is non-Delaunay, and I've represented the dome of sigma here in blue, that is above the dome of alpha. And now, to a simplex sigma that is not necessarily Delaunay, to any simplex sigma, we can associate another weight, which we can call the perfect weight of sigma, which is obtained as follows. To each point x in the convex hull of sigma, we look at the simplex, at the Delaunay simplex alpha that covers x, and we replace the height of the dome of sigma in the integral here by the height of the dome of alpha. So we replace the blue region here, the Delaunay weight in blue, by the yellow region there, which is the yellow region, which is whose volume is the perfect weight. And so by construction, the Delaunay weight is always larger than the perfect weight. And so this inequality translates in terms of energy. That is, the Delaunay energy of a triangulation T by construction is going to be larger than the perfect energy of a triangulation T, in which for the weights, we use the perfect weights. But this coincides with the Delaunay energy of the Delaunay complex, and we can prove that there is equality if and only if the triangulation T coincides with the Delaunay complex. So this is the idea in the Euclidean case. So in the Euclidean case, yeah, plus when now gamma is a D chain, normalized, the same remains true. So we have exactly the same sequence of inequalities here. So really, so now how to extend this when we are not in the Euclidean case? So in the Euclidean case, you have points that are D there. You have your D flat in some high dimensional space Rn. And you have the Delaunay complex there. But now, if you introduce some curvature, that is now the points that are not on a D flat, but they are on a D-dimensional submanifold, you have a problem, because how to compare simplices? You take a simplex sigma that is not in the Delloc complex, a complex simplex alpha that is in the Delloc complex, but how do you compare their domes? How do you define even a perfect weight in that case? Okay, so for the perfect weight, it seems the right things to do seems to take a point y in the convex hull of sigma, to project y onto the manifold M, and because the Delloc complex is a faithful reconstruction, it's going also to, there's going to be a point x in the Delloc complex, which will share with y the same projection M. So we can map a point of sigma y to a point x in the Delloc complex. And so we can replace for the perfect weight, we can do the same trick. We can replace the height in the integral here. We can replace the height of the dome at point y in sigma by the height of the dome alpha here at point x. But how do we know that the Delaunay weight is larger than the perfect weight? How can we be sure of that? And actually, it's not always true, because the problem is that we have to compare the two. We have to make a change of variable. And so to be able to compensate for this change of variables that is going to introduce some distortion, we need the point set P to be sufficiently safe. And because it's going to be sufficiently safe, we're going to have a margin of security to compare the domes. And so this is the idea. The idea of the proof.
I love the pictures with the domes, you know, and the blue dome above the pink dome. It reminds me of the Sydney Opera House almost.
So I have another question. So as far as I remember, there are other older literatures capturing the topology from the underlying manifold from the sampling. For example, the Rashep, I think Rashep proved that if the underlying sampling P is dense enough, then the virtuous complex of X is homotopy equivalent to M. Also,
Yes.
I think there's a paper by Smale and Yogi proved that under some conditions,
Yeah.
the check
Yes.
like homotopy equivalent to M. So can you compare your result with other older results? I think one advance definitely one of them.
Here, what is different is that, okay, can I go to the beginning? So all those constructions, you can locate them here. And what they say is that under some conditions that are much easier, you don't need, in particular, those safety conditions. But you get something that it's much weaker. You have the homotopy equivalence.
Yes, yeah. I think that's the strongest
But
point.
the price you have to pay, so far, we don't know how to do better, but the price you have to pay to get homeomorphism is to add those strange safety conditions. Yeah. But yeah, everything you said is correct. You know that the alpha complex, the Rips complex, the union of moles, all those constructions are going to capture the homotopy type. What is kind of nice here for this result, you don't need to assume that K has the homotopy type. It may not have actually the homotopy type. That's not a problem.
So you mean the K doesn't need to have the same homotopy type, the original manifold?
No, it does not. It does not.
Okay.
You can take, for instance, to build K, you can take the Delloc complex, and then you can add some additional simplices in K, assuming they are rho small, not too big. So you may create some extra topology there, but the result will still be homeomorphic. So the chain that minimizes the Delaunay energy will still be homeomorphic because you will retrieve the Delloc complex.
Okay. Yeah, that's quite unexpected, actually, at least to me.
That is unexpected or expected?
Unexpected, at least to me.
Yeah.
Okay, thank you. Yeah, it's very good to know. Yeah. Okay, any other questions?
Yeah, I had another question. So you mentioned computational complexity briefly at the end. I mean, so you're thinking more, well, I guess I'm interested both theoretically, you know, like the computational complexity, but also practically. So you computed this variational approach on some examples. Was that quite time consuming? Or?
Oh, well, yeah, it was time consuming because it was the beginning. I was not personally, we were not understanding what to do exactly. So I played with the Rips complex. So I'm going to put it. The problem is that when we are in small dimensions like this, the Rips complex becomes huge. So what we did, we would have to redo that and to optimize the code, because first of all, for small dimensions, it's much better to start, for instance, with something smaller like the Delaunay complex intersected by the Czech complex or something like this. And then maybe if we do the optimization in the right way, it would be interesting to see if it can be competitive with other methods that compute a surface, like the wrap complex. So maybe not, maybe it can never be, but also in high dimension, yeah, that would be interesting.
Thank you.
Play with that, but don't know how yet.
Thank you.
Okay.
Yeah.
Thank you. So let me stop the recording, but feel free to ask.
There
You
is
have
one question.